Tonight, we are going to explore one of the quietest revolutions in modern science. Not a discovery that announced itself with explosions, spectacular images from deep space, or headlines declaring that everything we know has changed overnight. Instead, this story begins with something almost impossibly small, a tiny particle, invisible to every human eye, drifting into existence for only a few millionths of a second before disappearing forever. A particle so insignificant that billions of them pass through your body every second without leaving the slightest trace. And yet this nearly invisible visitor may be carrying one of the greatest secrets the universe has ever hidden. Imagine spending decades building the most accurate scientific description of reality ever created. Imagine constructing a theory capable of predicting the behavior of matter with such astonishing precision that its calculations match experiments to 10 or even 11 decimal places. A theory that successfully explains the light entering your eyes, the atoms inside your body, the nuclear reactions inside stars, and the invisible forces that shape every object around you. A theory so successful that generations of physicists began to believe they were slowly approaching the final blueprint of nature itself. Now imagine discovering a tiny crack, not a dramatic collapse, not an obvious contradiction, just a whisper, a number that refuses to behave exactly as it should, a measurement that drifts ever so slightly away from prediction, so slightly that if you wrote both numbers on paper, they would appear almost identical. Yet buried deep within those endless decimal places lies a disagreement that has occupied thousands of scientists for decades. Sometimes the universe does not reveal its mysteries through enormous events. Sometimes it whispers them so quietly that only extraordinary patience allows us to hear. The particle at the center of this mystery is called the muon. Most people have never heard of it. Unlike electrons, protons, or neutrons, the muon does not make up the ordinary matter surrounding us. It is not responsible for chemistry, biology, or the familiar structure of everyday life. It simply appears briefly, usually born from violent collisions high above Earth's atmosphere, before decaying almost immediately into lighter particles. If the universe were a great orchestra, the muon would seem like a musician who walks onto the stage for only a single note before quietly leaving again. It appears unnecessary, almost accidental, yet nature rarely wastes effort. The more physicists studied the muon, the stranger it became. In almost every measurable way, it behaves like a heavier version of the electron. It carries the same electric charge. It possesses the same quantum spin. It obeys the same physical laws. The only obvious difference is its mass. A muon weighs approximately 207 times more than an electron. Why nature would create two nearly identical particles, differing mostly by weight, remains one of the unanswered questions of modern physics. Even today, nobody truly knows. Perhaps the muon exists simply because it can. Perhaps it is a leftover feature from conditions that existed shortly after the Big Bang. Or perhaps its existence hints at layers of reality that our current theories only partially reveal. For many decades, this mystery remained little more than an interesting curiosity. Then physicists began measuring something astonishingly delicate. Every charged particle behaves like a tiny magnet, not because it contains little pieces of metal, but because electric charge and quantum spin together create an intrinsic magnetic property. Even though these particles are unimaginably small, they respond to magnetic fields with remarkable precision. The standard model of particle physics, humanity's most successful scientific theory, predicts exactly how strong this tiny magnetic property should be. Not approximately, exactly. Or at least as exactly as mathematics allows. When physicists performed the calculations, they obtained an extraordinarily precise prediction for the muon's magnetic behavior. Every known particle contributes a tiny correction. Every known force leaves its fingerprint. Quantum mechanics, electromagnetism, the weak nuclear force, even fleeting virtual particles that exist only for unimaginably brief moments all play their part. The final prediction became one of the most precise calculations ever produced by human beings. Then the experiments began. The measurements themselves required decades of technological development. They demanded magnets of extraordinary uniformity, detectors capable of measuring events lasting only millionths of a second, and computers able to analyze billions upon billions of particle decays. Finally, after years of effort, the answer appeared, and it did not quite agree. The disagreement was unbelievably small, smaller than 1 part in a billion. To most people, such a tiny difference would seem meaningless. Surely every measurement contains tiny errors. Surely no experiment can be perfect. Ordinarily, that would be true. But particle physics has learned something remarkable over the past century. Nature is astonishingly precise. When experiments and theory disagree by even the smallest amount, history has shown that something profound is often waiting beneath the surface. The discovery of quantum mechanics began with tiny discrepancies. The theory of relativity emerged because minute inconsistencies refused to disappear. Entire revolutions have started with differences so small they could fit comfortably inside the last decimal place of a calculation. The universe, it seems, often hides its greatest secrets where almost nobody thinks to look. What makes this story even more fascinating is that empty space itself is not actually empty. When most of us imagine a vacuum, we picture absolute nothingness, a perfect emptiness stretching endlessly in every direction, a place where absolutely nothing exists. Quantum physics paints a completely different picture. According to our best understanding, even the emptiest region of space is alive with activity. Invisible fields constantly fluctuate. Pairs of particles briefly emerge from the vacuum before annihilating almost immediately. Energy flickers into existence and disappears again, following the strange rules allowed by quantum uncertainty. The vacuum is less like an empty room and more like the surface of a restless ocean. Even when it appears perfectly calm from a distance, microscopic waves are constantly rising and falling beneath the surface. The muon moves through this invisible sea. Every virtual particle that briefly appears around it subtly influences its magnetic behavior. Every known force leaves an almost unimaginably small imprint. But if unknown particles also exist, if entirely new forms of matter quietly inhabit this quantum ocean, then they too would influence the muon. Not dramatically, not enough for us to notice directly, but enough to shift one tiny number buried deep inside a long string of decimals. Perhaps that is exactly what physicists have been seeing all along. Perhaps the muon is not malfunctioning. Perhaps it is simply responding to parts of reality that we have not yet discovered. And to understand why such an incredibly tiny difference could reshape our understanding of the entire universe, we first need to step back and ask a much deeper question. What is the universe actually made of? To understand why a tiny particle like the muon could challenge one of humanity's greatest scientific achievements, we first have to step away from particle accelerators, superconducting magnets, and quantum equations. We need to return to one of the oldest questions our species has ever asked. Long before telescopes pointed toward distant galaxies or laboratories probed the smallest particles, people looked at the world around them and wondered what everything was ultimately made of. The question seems almost childlike in its simplicity. If you kept breaking things apart forever, would you eventually arrive at something that could no longer be divided? Would there be a final ingredient from which everything else emerged? Thousands of years ago, this was not merely a scientific question, it was a philosophical one. Ancient civilizations searched for patterns in nature, hoping that beneath the overwhelming complexity of everyday life, there existed a hidden simplicity. The Greeks imagined that everything was composed of earth, water, air, and fire. Other cultures proposed different combinations of fundamental elements, but the underlying intuition remained remarkably similar. They believed that reality itself possessed an elegant structure, waiting to be uncovered. In a sense, they were correct. Reality does seem to become simpler the deeper we investigate it, but it also becomes stranger. If you pick up a stone from the ground, it appears solid, permanent, and continuous. Your senses tell you that it is exactly what it seems to be. Yet every scientific breakthrough over the past few centuries has slowly stripped away that comforting illusion. Chemistry revealed that the stone is made of countless atoms. Physics later showed that atoms themselves are mostly empty space. Even the particles inside those atoms turned out not to be solid objects in the traditional sense, but excitations of invisible quantum fields extending throughout the universe. The deeper we look, the less familiar reality becomes. This gradual unraveling of matter is one of the greatest intellectual adventures in human history. For centuries, atoms were believed to be indivisible. The very word atom comes from the Greek word meaning uncuttable. They were imagined as the smallest possible building blocks of existence, tiny, eternal objects from which everything else was constructed. Then, near the end of the 19th century, that certainty disappeared almost overnight. In 1897, the British physicist J.J. Thomson discovered the electron. Suddenly, the atom was no longer indivisible. It possessed internal structure. Something even smaller existed inside what had once been considered fundamental. This discovery transformed science forever, not because electrons immediately explained everything, but because they demonstrated that nature always seemed willing to reveal another hidden layer. Only a few years later, another remarkable experiment changed our understanding once again. Ernest Rutherford famously directed alpha particles toward an incredibly thin sheet of gold. According to the accepted model of the time, those particles should have passed almost straight through with only minor deviations. Most of them did, but a tiny fraction behaved in a completely unexpected way. Some bounced backward. It was as though someone had fired a cannonball at a piece of tissue paper and watched it rebound toward the cannon itself. Rutherford later remarked that it was one of the most astonishing moments of his scientific career. The only explanation was that nearly all of an atom's mass was concentrated within an extraordinarily tiny nucleus. The atom was not a miniature solid sphere. It was mostly empty space. Imagine enlarging an atom until its nucleus became the size of a marble sitting at the center of a vast football stadium. The electrons would occupy regions near the outer edges, while almost everything in between would be empty. Not empty in the everyday sense. Quantum fields still fill that space. Electromagnetic forces still dominate its behavior. But in terms of ordinary matter, almost nothing is actually there. Everything you touch, every mountain, every ocean, every planet, every star, and even your own body is built primarily from emptiness structured by invisible forces. That realization alone fundamentally changes how we perceive reality. Solid objects do not truly touch each other. When your hand rests on a table, the electrons inside your skin repel the electrons inside the wood through the electromagnetic force. What feels like contact is actually an invisible force field preventing atoms from occupying the same space. The sensation of solidity emerges from interaction, not physical contact. Reality becomes increasingly abstract the more closely we examine it. As physicists continued exploring atomic structure throughout the early 20th century, they discovered that nuclei themselves contained additional particles. Protons carried positive electric charge, while neutrons carried none at all. At first, this seemed wonderfully satisfying. Perhaps these three particles, electrons, protons, and neutrons, were finally the true building blocks of existence. Three simple ingredients capable of explaining every material object in the universe. Chemistry suddenly became understandable. Different elements existed because they contained different numbers of protons inside their nuclei. Hydrogen possessed 1 proton. Helium contained 2. Carbon contained 6. Gold contained 79. The periodic table transformed from a collection of mysterious substances into a logical consequence of atomic structure. Everything appeared to fit beautifully together. Science often progresses this way. A puzzle grows increasingly complicated until suddenly a deeper pattern emerges that makes everything appear obvious in retrospect. For a brief moment, physicists believed they had reached something close to the bottom. Then the universe surprised them again. As particle accelerators became more powerful during the middle of the 20th century, scientists began smashing particles together at ever greater energies. They expected perhaps a handful of new discoveries. Instead, they uncovered an explosion of entirely unfamiliar particles. Kaons, pions, lambda particles, sigma particles, omega particles. Dozens upon dozens of strange, unstable objects appeared during high-energy collisions, before disappearing almost instantly. The simplicity that physicists had hoped for seemed to vanish. Instead of three fundamental particles, reality appeared crowded with an ever-growing zoo of exotic species. Some physicists joked that every newly discovered particle should result in a financial penalty rather than a Nobel Prize. The joke reflected genuine frustration. If every experiment simply uncovered more particles, would the search for fundamental simplicity ever end? For years, no one knew. Then another beautiful pattern emerged. The growing particle zoo was not actually composed of hundreds of unrelated building blocks. Most of these newly discovered particles turned out to be combinations of something even smaller: quarks. Unlike electrons, quarks never exist freely in ordinary nature. They remain permanently confined inside larger particles through one of the strongest forces known in physics. A proton consists of two up quarks and one down quark. A neutron contains one up quark and two down quarks. Suddenly, the enormous collection of mysterious particles became understandable. Nature had not become more complicated after all. It had simply revealed another hidden layer. This process repeats throughout the history of science. Every time reality appears overwhelmingly complex, patient observation eventually uncovers deeper simplicity hiding beneath the surface. At least, that has usually been the story. Because eventually physicists encountered a different kind of mystery. Not another hidden particle, not another deeper layer, but something that refused to fit naturally into the elegant pattern they had uncovered. Among all these newly discovered particles sat the muon. It behaved almost exactly like an electron. It possessed identical charge, identical spin. It interacted through the same forces. Yet it was over 200 times heavier. Unlike protons or neutrons, it played no obvious role in building ordinary matter. Unlike quarks, it was not required to explain atomic nuclei. Unlike photons, it did not carry forces between particles. It simply existed. Nature had apparently copied one of its fundamental particles almost perfectly, increased its mass dramatically, and offered no explanation whatsoever. Even today, physicists still ask the same question that echoed through laboratories nearly a century ago. Why? Perhaps the answer lies hidden inside the same tiny discrepancy that continues to puzzle researchers today. Because before we can understand why the muon refuses to behave exactly as predicted, we first need to understand the extraordinary theory that predicted its behavior so successfully in the first place. The standard model of particle physics is often described as humanity's greatest scientific achievement, and the deeper you look into its astonishing accuracy, the more incredible that description becomes. The standard model of particle physics is one of those rare achievements that almost feels impossible when you stop to think about it. It is not simply another scientific theory among many. It is the result of generations of physicists working across continents and decades, slowly assembling a mathematical description of reality, piece by piece, until an astonishing picture emerged. Every experiment, every calculation, every unexpected discovery gradually became part of a framework so accurate that it continues to withstand nearly every challenge nature has thrown at it. If you were somehow able to strip away everything familiar from the universe, removing every planet, every galaxy, every living creature, every grain of sand, and every drop of water until only the most fundamental ingredients remained, the standard model claims to tell you exactly what would be left. Remarkably, the list is far shorter than most people imagine. At first glance, the visible universe appears unimaginably complicated. Forests, oceans, mountains, clouds, stars, black holes, DNA, human brains, computers, crystals, lightning, and countless other phenomena all seem entirely different from one another. They possess different shapes, behaviors, temperatures, colors, and histories. Yet beneath that diversity lies extraordinary simplicity. According to the standard model, every object you have ever seen is built from only a handful of truly fundamental particles, interacting through a small number of equally fundamental forces. This is perhaps one of the deepest lessons modern physics has uncovered. Complexity does not necessarily require complicated ingredients. Sometimes astonishing richness emerges from surprisingly simple rules. Think about language. The English language contains hundreds of thousands of words. Entire libraries have been written using those words. Every novel, every scientific paper, every poem, and every conversation emerges from combinations of only 26 letters. Music works in much the same way. An entire symphony orchestra, capable of producing overwhelming emotional experiences, is ultimately arranging only 12 notes in different ways. Nature seems to operate according to a remarkably similar principle. The countless forms surrounding us emerge from an unexpectedly small collection of building blocks. The first family of these building blocks is known as quarks. There are 6 varieties, charmingly referred to as flavors by physicists. They are called up, down, charm, strange, top, and bottom. The names themselves sound almost playful, as though nature possesses a quiet sense of humor. Yet behind those whimsical labels lies mathematics of extraordinary precision. Only 2 of these quarks are required to build nearly everything you encounter in daily life: up quarks and down quarks. 2 up quarks combined with 1 down quark create a proton. 1 up quark combined with 2 down quarks creates a neutron. Those protons and neutrons form atomic nuclei. The nuclei combine with electrons. Atoms emerge. Chemistry follows. Stars ignite. Planets condense. Life eventually appears. Everything familiar unfolds from those incredibly simple beginnings. The remaining 4 quarks certainly exist, but they are generally too unstable to survive for long under ordinary conditions. They briefly appear during extremely energetic collisions inside particle accelerators or violent astrophysical environments before rapidly transforming into lighter particles. In a sense, they are reminders that nature is capable of producing far more possibilities than everyday experience reveals. The second family of fundamental particles is called the leptons. Here we finally meet an old acquaintance, the electron. Without electrons, there would be no chemistry, no molecules, no electricity flowing through your nervous system, no chemical bonds allowing DNA to exist. Electrons quietly shape nearly every process required for life itself. Yet electrons are not alone. Just as quarks come in 6 varieties, leptons also appear in 6 forms: the electron neutrino, the muon neutrino, the tau particle, and the tau neutrino. Immediately, something curious becomes apparent. Nature appears to repeat itself. The muon behaves almost exactly like a heavier electron. The tau behaves almost exactly like a much heavier electron again. Why? Nobody knows. This is one of those questions that quietly sits at the edge of modern physics, waiting patiently for an answer that has not yet arrived. Why would reality create 3 generations of nearly identical particles? Why stop at 3? Why not 1, or 5, or infinitely many? The Standard Model describes this repetition perfectly. It does not explain it. That distinction is important. Science often progresses by first describing patterns accurately before understanding why those patterns exist. Isaac Newton successfully described gravity centuries before Einstein explained it more deeply. Likewise, the Standard Model maps reality with breathtaking precision while leaving certain profound questions unanswered. Matter alone, however, is not enough to build a universe. The particles must also interact. For that, nature employs force carriers. Imagine children standing across a field, throwing balls to one another. Every throw transfers momentum from one child to another. In particle physics, something remarkably similar happens, except instead of visible balls, particles exchange invisible force-carrying particles known as bosons. When charged particles attract or repel one another, they exchange photons. These photons are the carriers of electromagnetism. Every beam of sunlight reaching Earth, every radio signal crossing continents, every Wi-Fi connection, every rainbow, every reflection, every chemical bond, every electrical impulse inside your brain, all arise from this single force. Then comes the strong nuclear force. It is carried by particles called gluons. The name is wonderfully descriptive. They literally glue quarks together. Without gluons, protons would immediately fall apart. Atomic nuclei could never exist. No atoms, no stars, no planets, no life. Everything familiar depends upon these invisible messengers continuously binding quarks together with unimaginable strength. The weak nuclear force performs an entirely different task. Carried by the W and Z bosons, it governs radioactive decay and enables the nuclear reactions powering stars like our sun. Every second, deep within the solar core, hydrogen atoms transform into helium through processes involving the weak interaction. Tiny differences in mass become enormous quantities of energy, according to Einstein's famous equation. The sunlight warming your face today began as weak nuclear interactions occurring hundreds of thousands of years ago inside the dense interior of the sun before slowly making their journey outward. Even our existence depends upon this subtle force quietly operating beyond human perception. Finally comes, perhaps, the most famous addition to the Standard Model, the Higgs field. For decades, physicists suspected that something invisible permeated every corner of space, interacting continuously with fundamental particles. Without this field, electrons would possess no mass, quarks would possess no mass, atoms could never form, matter itself would fail to exist. Imagine trying to build a house using bricks that forever moved at the speed of light. Construction would be impossible. The Higgs field changes everything. Particles moving through it acquire mass, almost as though they experience resistance while traveling through an invisible cosmic medium. The discovery of the Higgs boson in 2012 represented one of the greatest experimental triumphs in modern science because it confirmed the existence of this remarkable field that quietly fills the universe around us. Yet perhaps the most astonishing feature of the Standard Model is not what it contains. It is how astonishingly accurate it has proven to be. Again and again, physicists have calculated properties of particles before measuring them experimentally. Again and again, nature has agreed. The masses of new particles, the strengths of interactions, the probabilities of exotic decays, the outcomes of unimaginably complex collisions. Everything kept matching, sometimes to 10 or 11 decimal places. It is difficult to appreciate just how extraordinary this level of agreement truly is. Imagine predicting the distance between Amsterdam and Sydney with an error smaller than the width of your fingernail. Imagine forecasting the exact arrival time of every wave reaching a beach years into the future. Imagine calculating every leaf that would fall from every tree during the next autumn. Those analogies still fail to capture the astonishing precision achieved by the Standard Model. For decades, nature appeared almost eager to confirm every prediction physicists made. The theory survived, experiment after experiment. Whenever researchers searched for flaws, they instead found further confirmation. It became tempting to believe that perhaps humanity had finally discovered the deepest laws governing reality itself. But even while celebrating its extraordinary success, physicists quietly recognized something unsettling. The Standard Model could not possibly be complete. It contains no explanation for gravity. It cannot account for the invisible dark matter shaping galaxies. It says almost nothing about the mysterious dark energy accelerating cosmic expansion. It offers no satisfying explanation for why the universe contains far more matter than antimatter. Nor does it explain why there are exactly 3 generations of particles. It is astonishing, but incomplete. Rather like possessing an incredibly detailed map that perfectly describes every street inside a city while remaining completely silent about the surrounding continent. Physicists knew another layer almost certainly existed. The question was how to find it. One possibility was obvious: build larger particle accelerators, smash particles together with greater energy, hope entirely new particles emerge. The other possibility was far more subtle. Perhaps new physics was already influencing familiar particles in almost imperceptible ways. Perhaps reality was whispering rather than shouting. And among every known particle, one seemed uniquely suited to hear those whispers: the muon. The muon is, in many ways, an unlikely hero. If you asked someone to guess which particle might one day reveal a crack in our understanding of the universe, they would probably choose something dramatic. Perhaps the Higgs boson, with its connection to mass itself, or a black hole whose gravity bends both space and time. Maybe even an entirely hypothetical particle that has never been observed before. Very few people would point toward the muon. It does not build the atoms inside your body. It is not responsible for holding nuclei together. It is not the particle carrying light across the universe. It simply appears, lives for about 2/millionths of a second, and then disappears forever. From nature's perspective, it almost seems temporary. And yet temporary things can leave permanent clues. The muon was first discovered in 1936, while physicists were studying cosmic rays, the constant stream of energetic particles arriving from outer space. Long before satellites explored distant planets, Earth itself served as a natural detector for the violent events occurring throughout the galaxy. Every second, particles accelerated by exploding stars, distant supernova remnants, and perhaps even supermassive black holes race through space at astonishing speeds. When they collide with Earth's atmosphere, they create enormous cascades of secondary particles. Invisible showers spread downward through the atmosphere, producing countless exotic particles that briefly flash into existence before disappearing again. One of those particles was the muon. When researchers first observed it, confusion quickly followed. Its electric charge matched that of the electron perfectly. Its spin matched. Its behavior under electromagnetic forces matched. Everything suggested it was simply another electron. Except it wasn't. It was over 200 times heavier. That single difference changed everything. Initially, some physicists believed the muon might solve another outstanding mystery. Around the same period, Japanese physicist Hideki Yukawa had proposed the existence of a medium-mass particle responsible for carrying the strong nuclear force. The masses seemed similar enough that many assumed the newly discovered muon must be Yukawa's predicted particle. It was an understandable conclusion, but nature had another surprise waiting. Further experiments revealed that the muon barely interacted with atomic nuclei at all. Instead of behaving like the carrier of the strong force, it passed through matter with astonishing ease. In fact, thousands of muons generated high in Earth's atmosphere pass directly through your body every minute without causing any noticeable effect. Most continue through buildings. Many continue through mountains. Some even pass through hundreds of meters of rock before finally decaying. They are ghostly travelers, almost indifferent to the ordinary matter surrounding them. The famous physicist, Isidore Isaac Rabi, reportedly reacted to the muon's discovery with a sentence that has become legendary within physics. Who ordered that? The question was partly humorous, but beneath the joke lay genuine scientific bewilderment. Why would the universe contain a particle that seemed almost identical to an electron while serving no obvious purpose? Even today, nearly a century later, the question remains unanswered. Perhaps nature is under no obligation to justify itself. Perhaps every particle exists because the mathematical structure of the universe permits it. Or perhaps the muon exists precisely because it serves as a messenger, revealing aspects of reality that lighter particles cannot perceive. Ironically, the very property that once made the muon seem unnecessary, its greater mass, is exactly what eventually transformed it into one of the most important particles in modern physics. To understand why, we need to think differently about empty space. Most people imagine the vacuum as complete nothingness, a perfect absence, a region where absolutely nothing exists. Quantum field theory tells a profoundly different story. According to our best understanding, every point in space is filled with invisible fields, electromagnetic fields, electron fields, quark fields, Higgs fields, neutrino fields. Every known particle corresponds to a quantum field extending throughout the entire universe. Particles are not separate from these fields. They are tiny excitations of them, like ripples traveling across the surface of an ocean. Even when no visible particles are present, These fields never become completely still. They fluctuate, they vibrate, they continuously exchange energy according to the strange rules of quantum mechanics. For unimaginably brief moments, pairs of virtual particles appear and disappear. These particles are not directly observable. They cannot be captured. They cannot be isolated. Yet their effects are measurable. This is one of the strangest ideas in all of physics. Things that cannot be directly observed nevertheless influence measurable reality. Imagine standing beside a perfectly calm lake at night. You cannot see the tiny currents flowing beneath the surface. Yet if a small leaf drifts across the water, its motion quietly reveals those invisible movements. The leaf becomes a messenger for processes hidden below. The muon behaves much like that leaf. As it moves through space, every virtual particle surrounding it subtly alters its magnetic properties. Virtual photons contribute. Virtual electrons contribute. Virtual quarks contribute. Virtual W bosons contribute. Virtual Higgs bosons contribute. Everything the standard model contains leaves an incredibly tiny fingerprint upon the muon's magnetic behavior. The astonishing part is that physicists know how to calculate nearly all of those fingerprints. Every contribution, every correction, every interaction. The mathematics becomes almost unimaginably complicated, involving thousands upon thousands of quantum processes occurring simultaneously. Yet after decades of work, theorists succeeded. The prediction became extraordinarily precise. Imagine listening to an orchestra where every musician performs perfectly. Each instrument contributes exactly the correct note at exactly the correct moment. Now imagine hearing a single additional note, almost inaudible, so quiet that only the most sensitive microphone could detect it. That single unexpected note would immediately tell you another musician was playing somewhere beyond your view. The muon's magnetic moment functions almost exactly like that microphone. It listens to the entire quantum universe simultaneously. If an unknown particle exists anywhere within the fabric of reality, even one far too massive to produce directly inside today's accelerators, it can briefly appear as a virtual particle. For an unimaginably tiny fraction of a second, it may influence the Muon before disappearing again. The Muon cannot identify what the particle is. It cannot reveal its name. It cannot tell us its mass directly, but it can tell us that something unexpected has joined the orchestra. This is why physicists became obsessed with measuring one seemingly insignificant number, the muon's magnetic moment. More specifically, its anomalous magnetic moment. At first glance, the terminology sounds intimidating. In reality, the underlying idea is surprisingly elegant. Every spinning charged particle behaves like a tiny compass needle. If placed inside a magnetic field, it begins to rotate. The exact speed of that rotation depends upon the particle's magnetic properties. For an ideal particle, simple quantum mechanics predicts a specific value, a number physicists call g. For a perfectly simple particle, g should equal exactly 2. Nature, however, is rarely that simple. Because of all those invisible, virtual particles flickering throughout space, the actual value differs slightly. Not by much. Just enough to reveal that the quantum vacuum itself is constantly participating. The tiny difference between the ideal value and reality is called the anomalous magnetic moment. It is extraordinarily small. Yet, hidden inside that tiny correction lies the combined influence of every known particle in existence, and perhaps every unknown particle as well. This is what makes the muon uniquely powerful. The heavier a particle becomes, the more strongly it feels the influence of heavy virtual particles surrounding it. The electron is much lighter. Its magnetic moment has actually been measured even more precisely than the muon's. But because it weighs so little, it is comparatively insensitive to potential new physics. The tau particle, another heavier cousin of the electron, would in theory be even better than the muon. Unfortunately, it decays far too quickly. Scientists cannot study it with sufficient precision. The muon sits perfectly between those extremes, heavy enough to notice hidden particles, stable enough to measure. It occupies an almost miraculous position. Not too light, not too unstable, just right. Sometimes it almost feels as though nature deliberately left us one ideal messenger, one particle capable of revealing secrets hidden just beyond the reach of our current understanding. But possessing the perfect messenger was only the beginning. The real challenge was learning how to interrogate it. How do you measure the magnetic behavior of a particle that lives for barely 2 millionths of a second? How do you achieve precision measured in parts per billion before the particle vanishes forever? Answering that question required one of the most extraordinary experiments ever constructed. It involved a gigantic superconducting ring, billions upon billions of muons, and an engineering achievement so unusual that moving a single piece of equipment across the United States became an international event in its own right. There is something almost poetic about the fact that one of the most important experiments in modern physics depends upon watching a particle that hardly has time to exist. The average human blink lasts roughly 300 milliseconds. A muon survives for about 2 millionths of a second. In the time it takes your eyelids to close and open once, more than 100,000 generations of muons could be born, live out their entire existence, and vanish forever. How do you study something so fleeting? How do you ask meaningful questions of a particle that seems determined to disappear before you can even observe it? For decades, physicists wrestled with exactly this problem. The answer eventually became one of the most elegant experiments ever conceived. Imagine holding a spinning gyroscope in your hand. If you tilt it slightly, something fascinating happens. Instead of simply falling over, the spinning axis begins to slowly rotate around another direction. It traces a smooth circle through space. This motion is known as precession. Although the gyroscope appears stable, its axis quietly drifts. The same phenomenon occurs throughout nature. Earth itself slowly precesses. Its rotational axis traces an enormous circle across the sky over roughly 26,000 years. Because of this slow movement, the identity of the North Star gradually changes over immense periods of time. The muon behaves in a remarkably similar way. Although quantum spin is not literally a tiny object rotating through space, its mathematical behavior closely resembles that of a spinning top. Place a muon inside a magnetic field, and its spin begins to precess. It slowly rotates. It gently wobbles. It dances around the magnetic field with astonishing regularity. The exact speed of this precession depends upon the muon's magnetic moment. That simple relationship became the foundation of an extraordinary experiment. The challenge was creating an environment where trillions of muons could survive long enough for scientists to observe this tiny rotational dance. Physicists realized they needed an almost perfectly uniform magnetic field. Any tiny variation would slightly alter the muon's behavior, making the measurement less precise. The solution eventually took the form of a gigantic superconducting storage ring. Picture an enormous circular racetrack nearly 50 feet across. Instead of racing cars, it guides invisible particles traveling at almost the speed of light. Instead of asphalt, its boundaries are defined entirely by magnetic fields. Inside this ring, muons circle thousands of times before finally decaying. During those brief moments, every revolution quietly reveals another clue about the hidden structure of reality. Creating the muons themselves is an achievement of engineering. Scientists begin by accelerating protons to tremendous speeds using powerful particle accelerators. These energetic protons crash into a metal target with incredible force. The collision produces an explosion of secondary particles. Among them are particles called pions. Pions are unstable. Within only a few dozen billionths of a second, they decay naturally into muons and neutrinos. This process is remarkably fortunate. The muons emerge already polarized, meaning their quantum spins tend to point in similar directions. Without this natural alignment, the entire experiment would become vastly more difficult. Sometimes nature quietly assists those attempting to understand it. The freshly created muons are carefully selected and injected into the storage ring. They enter moving at approximately 99.94% of the speed of light. At such incredible velocities, Einstein's theory of relativity begins to influence the experiment in an unexpected and extremely helpful way. According to special relativity, moving clocks run more slowly. This phenomenon, known as time dilation, is no mere mathematical curiosity. It has measurable consequences. From our perspective inside the laboratory, the rapidly moving muons live significantly longer than they would at rest. Their internal clocks slow down. Instead of surviving only about 2 millionths of a second, they remain observable for roughly 64 millionths of a second. That still sounds unimaginably brief. Yet, in particle physics, it is a generous amount of time. Enough time for the muons to circle the storage ring thousands of times before decaying. Enough time to measure their behavior with astonishing precision. Without relativity, the experiment would scarcely be possible. One of Einstein's most famous theories quietly becomes an essential laboratory tool. As the muons race around the circular ring, two separate motions occur simultaneously. First, the particles themselves travel around the ring at nearly the speed of light. Second, their spins slowly precess inside the magnetic field. The key insight lies in the tiny difference between these two motions. If the muon's magnetic moment possessed exactly the simplest theoretical value, the spin would rotate at a very specific rate. But because quantum fluctuations continually influence the particle, the spin rotates ever so slightly faster. That minute difference contains the information physicists seek. Measuring it, however, presents another challenge. You cannot simply look at the spin of a muon. Quantum mechanics does not permit such direct observation. Instead, researchers exploit another remarkable feature of nature. When a muon eventually decays, it produces an electron, or, depending on the muon's charge, a positron, along with two neutrinos. Crucially, the highest energy electrons tend to emerge in the same direction the muon's spin happened to be pointing at the instant of decay. This subtle preference becomes the experiment's secret language. By recording the directions and energies of billions of decay electrons, scientists reconstruct the invisible motion of the muon's spins. It is almost like watching leaves carried downstream to infer the invisible currents flowing beneath the water. The leaves themselves are not the current, but they faithfully reveal its motion. Around the inside of the storage ring sit sophisticated detectors, known as calorimeters. Whenever an energetic electron strikes one of these detectors, it deposits its energy. Every impact is recorded with extraordinary precision. Billions of such events gradually accumulate into a delicate oscillating pattern. At first glance, the data appear almost beautiful. A slowly fading wave rises and falls with hypnotic regularity. Each peak corresponds to moments when many electrons arrive. Each valley marks moments when comparatively few appear. Hidden inside that gentle rhythm lies the precession frequency of the muon's spin. Extracting it requires years of analysis. The detectors must be calibrated constantly. Temperature changes can influence electronics. Tiny timing shifts must be corrected. Background signals removed. Random fluctuations carefully understood. Nothing may be taken for granted. But measuring the muons alone is only half the problem. To determine the anomalous magnetic moment, scientists must also know the magnetic field itself with astonishing accuracy. This requirement proved almost as challenging as observing the muons. Imagine trying to measure the depth of an ocean while the water itself is constantly shifting. Even the slightest variation in magnetic strength would subtly alter the muon's motion. A tiny imperfection could masquerade as entirely new physics. So researchers devoted extraordinary effort to mapping the magnetic field. Special probes based on nuclear magnetic resonance traveled carefully around the storage ring, measuring the field point by point. Hundreds of individual measurements were combined into an incredibly detailed three-dimensional map. Every bump, every ripple, every microscopic imperfection. Nothing escaped attention. Engineers adjusted tiny pieces of iron surrounding the magnets to smooth the field. Again and again, they repeated the measurements. Again and again, they refined the system. The level of precision borders on the unbelievable. Even thermal expansion caused by changing room temperature had to be monitored. Mechanical vibrations mattered. Minute electrical variations mattered. Incredibly, even the gravitational pull of the moon, our moon orbiting Earth, slightly influenced the apparatus through subtle deformations of the laboratory floor. When your goal is accuracy measured in parts per billion, almost nothing becomes too small to consider. This obsessive attention to detail reveals something beautiful about science. Great discoveries rarely emerge from dramatic moments alone. They emerge from patience, from thousands of small improvements, from relentless questioning, from refusing to accept uncertainty where greater understanding is possible. Every bolt tightened, every detector recalibrated, every correction independently verified, every assumption challenged. The final measurement becomes trustworthy, precisely because so many people spend years trying to prove it wrong. Only after surviving every attempt at criticism does a scientific result begin to earn genuine confidence. Eventually, after billions upon billions of recorded muon decays and countless hours of analysis, the experiment produced its answer. The oscillation frequency could be measured with astonishing precision. The magnetic field was known more accurately than almost anyone had once believed possible. Everything was finally ready. All that remained was comparing the measured value with the prediction of the standard model. If both numbers matched, one of the greatest theories ever created would once again emerge victorious. If they differed, then somewhere, hidden deep within the quantum vacuum, reality itself might be trying to tell us that our understanding of the universe was still incomplete. And when physicists finally placed those two numbers side by side, they discovered something that would occupy the next several decades of their lives. When the first complete measurements finally emerged, they did not arrive with fireworks. There was no single moment when every physicist in the world suddenly realized that the standard model had failed. There was no dramatic announcement declaring that a new law of nature had been discovered. Instead, the result appeared quietly, almost modestly, as a sequence of numbers printed inside a scientific paper. To anyone unfamiliar with particle physics, the difference seemed almost laughably small. Several decimal places, nothing more. It was the kind of discrepancy most people would instinctively dismiss. Surely every experiment contains tiny imperfections. Surely no measurement could ever be expected to agree perfectly with theory. Normally, that reasoning would be entirely correct. But particle physics is unlike almost every other branch of science. Its predictions are so extraordinarily precise that even unimaginably tiny disagreements demand attention. Imagine owning the world's most accurate clock. Not one that gains or loses a second every year. Not one that remains accurate for centuries. Imagine a clock so precise that it would lose only a single second over billions of years. Now imagine discovering that it consistently gains one extra tick every few months. The error would be almost impossible to notice. Yet if such a clock truly existed, that single unexpected tick would immediately suggest something remarkable. Not because the error was large, but because the clock itself was known to be extraordinarily reliable. The standard model is much like that clock. Its predictions have survived countless experimental tests over more than half a century. Again and again, physicists attempted to find cracks in its mathematical structure. Again and again, nature replied with astonishing agreement. New particles were discovered exactly where the theory predicted. Their masses matched expectations. Their interactions matched calculations. Entire generations of researchers devoted their careers to testing the standard model, and almost every time the theory emerged stronger than before. This long history made the Muon result profoundly unsettling, because the disagreement refused to disappear. The first truly high-precision measurements were performed at Brookhaven National Laboratory on Long Island, New York. Over several years, physicists accumulated billions of muon decays, carefully analyzing every possible source of experimental uncertainty. When the analysis was complete, the answer lay slightly above the theoretical prediction. Not dramatically, not enough to claim a revolutionary discovery, but enough to make people pause. Statistically, the discrepancy corresponded to approximately 3 standard deviations. To understand why that mattered, we need to briefly step into the world of probability. Whenever scientists perform experiments, random fluctuations naturally occur. Even if every instrument functions perfectly, repeated measurements never produce exactly identical results. Tiny variations arise simply because nature itself is probabilistic at the quantum level. Physicists therefore measure not only the value itself, but also how likely that value would appear by chance. This likelihood is expressed using something called sigma, or standard deviation. 1 sigma differences happen constantly. If you repeatedly measured the height of a large group of people, many values would naturally fall 1 sigma above or below the average. 2 sigma differences are less common, but still perfectly ordinary. 3 sigma becomes much more interesting. It corresponds to roughly a 1 in 350 chance that the observed discrepancy arose purely through random statistical fluctuations. That sounds impressive. Yet particle physicists have learned caution through painful experience. Throughout history, many 3 sigma anomalies have eventually disappeared after more data were collected. Some became famous. Some even generated headlines suggesting entirely new physics, only to quietly fade away a few years later when improved experiments revealed that the original discrepancy had simply been an unlikely statistical fluctuation. Because of this history, particle physicists adopted an extraordinarily demanding standard. Nothing is considered a genuine discovery until it reaches 5 sigma. 5 standard deviations correspond to roughly a 1 in 3.5 million chance of arising randomly. Only then do researchers begin speaking confidently about new physics. Brookhaven had reached roughly 3 sigma. Exciting, intriguing, far from conclusive. The physics community reacted exactly as science should. Not with celebration, not with dismissal, with skepticism. The result deserved investigation, nothing more. Many wondered whether some subtle experimental mistake had escaped notice. Perhaps the magnetic field had not been perfectly uniform. Perhaps tiny detector effects had introduced hidden biases. Perhaps some overlooked correction remained buried inside the enormous data analysis. Others questioned the theoretical calculations themselves. Could the standard model prediction contain hidden uncertainties larger than previously believed? Every possibility had to be examined. The only reliable solution was obvious. Repeat the experiment. Not simply using the same equipment, using different scientists, different detectors, different analysis techniques, independent confirmation. Only then could anyone begin trusting the result. This decision eventually led to one of the most extraordinary engineering projects in recent scientific history. The heart of the Brookhaven experiment was an enormous superconducting storage ring, nearly 50 feet in diameter. Building another from scratch would have required years and enormous financial resources. Yet dismantling the original ring was impossible. Its delicate superconducting coils formed one continuous structure. Separating them would destroy the instrument. So physicists decided upon an alternative that sounded almost absurd. They would move the entire ring across the United States in one piece. The magnet weighed hundreds of tons. Its diameter exceeded the width of most roads. Bridges, tunnels, and overhead power lines all presented obstacles. Transporting it required months of planning, involving engineers, transportation specialists, police departments, and government agencies. The journey itself became almost legendary. The massive ring left Brookhaven under the cover of darkness, moving slowly along specially prepared roads before reaching a waiting barge. From there, it traveled down the Atlantic coast, around Florida, into the Gulf of Mexico, up the Mississippi River, then along inland waterways toward Illinois. Finally, after more than 3,000 miles of travel, it completed the last portion of the journey by road to Fermilab, just outside Chicago. Throughout the entire voyage, the ring had to remain nearly perfectly level. Even modest tilting could damage its delicate superconducting components. Sensors constantly monitored its orientation. Drivers proceeded with extraordinary caution. People gathered along roadsides simply to witness the surreal sight, an enormous circular magnet floating down rivers and creeping through quiet suburban streets in the middle of the night. It looked less like scientific equipment and more like some mysterious artifact transported from another civilization. Yet that strange procession carried humanity's best chance of answering one of physics' deepest questions. At Fermilab, the experiment received significant upgrades. The accelerator complex could now produce far more muons than Brookhaven ever managed. Improved detectors recorded particle decays with greater precision. Better tracking systems revealed subtle details about the muon beam itself. More sophisticated electronics reduced background noise. The magnetic field could be mapped more accurately than before. Perhaps most importantly, the researchers adopted an analysis technique known as blinding. This procedure is wonderfully simple. The scientists intentionally hide the final answer from themselves while analyzing the data. They cannot accidentally adjust methods to obtain the result they secretly hope for, because they literally do not know what the result is. Only after every correction, every calibration, every uncertainty, and every analysis decision has been finalized is the hidden offset removed. Only then does the true measurement appear. This remarkable practice reflects something essential about modern science. Scientists are not merely searching for confirmation. They are constantly protecting themselves from their own expectations. Human beings naturally see patterns where they hope patterns exist. Blinding helps remove that temptation. Years passed. More muons circulated through the storage ring. Billions became trillions. The analysis continued. Then, in 2021, Fermilab announced its first major result. The physics community watched closely. If the Brookhaven anomaly disappeared, decades of speculation would quietly come to an end. If it remained, everything would become considerably more interesting. The numbers appeared. They matched Brookhaven almost perfectly. Not exactly. No two independent experiments ever produce absolutely identical values, but astonishingly close. Close enough that the discrepancy became stronger rather than weaker. Two entirely separate laboratories, different equipment, different generations of scientists, different systematic uncertainties. Yet the same tiny disagreement persisted. The combined significance climbed above 4 sigma. Now the conversation changed. This no longer looked like an isolated experimental curiosity. Something genuine appeared to be hiding inside the measurement. Physicists around the world became increasingly excited. Could this finally be the first confirmed crack in the standard model? Had humanity discovered its first unmistakable hint of entirely new particles? The excitement grew with every additional dataset collected at Fermilab. Each new run improved the measurement. Each analysis reduced statistical uncertainty. Each publication reinforced the astonishing precision of the experimental result. The experimentalists had done something extraordinary. They had measured one tiny property of one tiny particle more accurately than almost anyone had previously imagined possible. Yet, an unexpected complication soon emerged. Ironically, it did not originate inside the laboratory. It emerged from the theorists themselves. Because while experimental physicists increasingly agreed about what nature was doing, theoretical physicists suddenly found themselves disagreeing about what the standard model actually predicted in the first place. At first, this seems almost impossible to imagine. How could the experiment be settled while the theory remained uncertain? Isn't science supposed to work the other way around? We usually picture scientists constructing a theory, making a prediction, and then performing an experiment to see whether reality agrees. If the measurement is accurate enough, the question should be answered. But nature is rarely so accommodating. Sometimes the experiment is easier than the mathematics. The muon's anomalous magnetic moment is one of those extraordinary cases. By the early 2020s, the experimental picture had become remarkably clear. Independent laboratories had measured the muon's behavior with breathtaking precision. Every imaginable systematic uncertainty had been investigated. Every detector had been calibrated repeatedly. Every source of potential error had been scrutinized for years. The measurement itself had become one of the most reliable numbers in all of particle physics. The remaining uncertainty no longer came primarily from the laboratory. It came from the equations. This surprises many people because mathematics is often imagined as perfectly exact. 2 plus 2 always equals 4. Geometry does not change its mind. A correctly solved equation produces only one answer. Quantum field theory is different. not because the mathematics itself is inconsistent, but because some of the calculations become so enormously complicated that solving them exactly remains beyond our current abilities. Imagine trying to predict the motion of every individual molecule inside a hurricane. The laws governing each molecule are well understood. The difficulty lies in solving all of them simultaneously. The strong nuclear force presents a similar challenge. Electromagnetism is comparatively gentle. Its effects weaken rapidly with distance, allowing physicists to calculate corrections one step at a time. Each additional quantum interaction contributes a smaller correction than the previous one. The mathematics behaves beautifully. The strong force refuses to cooperate. At the tiny distances relevant to quarks, it becomes unimaginably powerful. Instead of weakening, it effectively traps quarks together inside particles like protons and neutrons. Physicists call this confinement. No one has ever observed an isolated quark drifting freely through space. Nature simply does not allow it. This incredible strength creates a mathematical nightmare. Instead of tidy corrections that become progressively smaller, every interaction strongly influences every other interaction. The equations become tangled together in ways that resist straightforward calculation. It is rather like trying to predict the motion of every fish inside a violently swirling school, where each fish continuously changes direction in response to every nearby neighbor. The rules remain simple. The collective behavior becomes astonishingly difficult. The muon's magnetic moment receives tiny contributions from these incredibly complicated strong force interactions. Although those contributions are small overall, they are large enough to dominate the uncertainty in the final theoretical prediction. And that uncertainty suddenly became the center of one of modern physics' most fascinating debates. For decades, physicists had relied upon a method known as the data-driven approach. Rather than calculating every strong force interaction directly, they allowed nature to perform part of the calculation for them. This idea is surprisingly elegant. Instead of solving impossible equations, researchers measure related particle collisions inside accelerators. Specifically, they collide electrons with their antimatter counterparts, positrons. When these particles annihilate one another, they produce showers of strongly interacting particles. The rates of those reactions can then be inserted into powerful mathematical relationships, known as dispersion relations. Those relationships allow experimental data to determine the difficult portion of the muon calculation. It is almost like measuring the shadow of an invisible object instead of trying to observe the object directly. The shadow contains enough information to reconstruct what cannot easily be seen. For many years, this method worked beautifully. Different laboratories performed independent measurements. Different research groups analyzed the data. Their results largely agreed. Gradually, an international consensus emerged regarding the standard model prediction. When compared with Brookhaven and later Fermilab, the discrepancy appeared increasingly significant. Everything seemed to point toward new physics. Then something unexpected happened. Another group of physicists approached the problem from an entirely different direction. Instead of relying upon experimental collision data, they attempted something much more ambitious. They decided to calculate the strong force contribution directly from the fundamental equations themselves. At first glance, this sounds impossible. Earlier we saw why the equations become so difficult. The strong force refuses to yield simple solutions. So how could anyone hope to calculate it directly? The answer required one of humanity's greatest computational achievements. Researchers developed a technique called lattice quantum chromodynamics. The name sounds intimidating. The basic idea is surprisingly intuitive. Instead of treating space as perfectly continuous, they divide it into an unimaginably fine three-dimensional grid. Imagine replacing the smooth surface of a lake with billions upon billions of tiny squares. Quarks occupy the intersections. Gluons connect neighboring points. The entire quantum universe becomes a vast computational lattice. Inside this artificial universe, enormous supercomputers simulate every possible interaction. Again and again. Billions of times. Random quantum fluctuations are sampled. Average behaviors gradually emerge. As the grid becomes finer and the simulations become more sophisticated, the results approach what the actual universe should produce. It is a breathtaking combination of theoretical physics, computer science, and raw computational power. Some of these simulations consume hundreds of millions of processor hours, machines operating continuously for months, sometimes years. The calculations themselves become scientific expeditions, not unlike launching a spacecraft. Eventually, one collaboration, known as BMW, completed an especially precise lattice calculation. When they compared their prediction with the older data-driven value, something astonishing appeared. The numbers did not agree, not by a tiny amount, by enough to change the entire interpretation of the Muon experiment. The lattice calculation predicted a larger contribution from the strong force. That seemingly modest increase pushed the standard model prediction upward, closer to the experimental measurement, much closer. If the lattice calculation proved correct, the famous discrepancy almost disappeared. Suddenly, the muon no longer seemed to be pointing toward unknown particles. Instead, it appeared to agree remarkably well with existing physics. This was not a conflict between experiment and theory. It was a conflict between two different ways of performing the same theoretical calculation. One relied heavily upon experimental collision data. The other relied upon first principles computer simulations. Both approaches were grounded in sound physics. Both possessed compelling arguments, yet they produced noticeably different answers. It was as though two beautifully crafted maps of the same coastline refused to overlap. Neither could simply be dismissed. Neither could yet be fully trusted above the other. The situation became even more intriguing when additional lattice groups began publishing their own calculations. Some leaned toward the newer lattice result. Others remained less certain. Several possessed uncertainties, too large to settle the question decisively. Meanwhile, new collision experiments continued measuring the data required for the traditional approach. Some of those measurements also produced unexpected tensions. One experiment, known as CMD3, reported values differing noticeably from previous international measurements. If CMD3 proved correct, the traditional prediction would move closer to the lattice calculations. If earlier experiments proved correct, the discrepancy with the muon measurement would remain. Suddenly, the uncertainty had multiplied, not because science was failing, but because science was working exactly as it should. Different groups independently questioned one another. Independent methods challenged previous assumptions. Nobody accepted extraordinary conclusions without extraordinary scrutiny. This often surprises people outside scientific research. Science is sometimes portrayed as a collection of facts. In reality, it is an ongoing conversation. A remarkably disciplined conversation. Every calculation is questioned. Every experiment repeated. Every conclusion held tentatively until overwhelming evidence accumulates. Disagreement is not a weakness. It is one of science's greatest strengths. If every physicist immediately agreed with every new result, genuine mistakes would survive far longer. Healthy skepticism is the engine that gradually transforms uncertainty into knowledge. As the years passed, neither side completely convinced the other. The experimental measurements remained astonishingly consistent. The theoretical calculations steadily improved. New lattice simulations became more sophisticated. Fresh collision data continued arriving. Each advance clarified part of the puzzle, while simultaneously raising new questions. For those watching from outside, this uncertainty sometimes seemed frustrating. People naturally want simple answers. Is the standard model broken? Yes or no? Does the muon reveal new physics, or doesn't it? Nature rarely answers in such straightforward language. Instead, she offers clues, small clues, incomplete clues, pieces of a puzzle scattered across decades of work. Scientists slowly gather those pieces, knowing that certainty rarely arrives all at once. And yet, beneath all of this debate, one extraordinary possibility continued to capture the imagination of physicists around the world. Suppose the original discrepancy really was pointing towards something entirely new. Suppose the muon truly was sensing particles beyond the standard model. What kind of hidden universe would be capable of leaving such an incredibly subtle fingerprint? And if those unseen particles really exist, Could humanity ever hope to find them directly? If the muon's tiny discrepancy truly represents new physics, then somewhere beyond the standard model, there must exist particles or forces that humanity has never observed directly. They would not simply be additions to our list of known particles. They would represent an entirely new layer of reality, one that has quietly existed alongside everything we have ever studied without revealing itself openly. That possibility is both thrilling and humbling. Throughout the history of science, every major revolution has followed a similar pattern. First came the anomaly, then years of uncertainty. Finally, after enough evidence accumulated, an entirely new picture of reality emerged. Mercury's unusual orbit eventually led to general relativity. The ultraviolet catastrophe helped give birth to quantum mechanics. Unexpected radioactivity shattered the belief that atoms were indivisible. Again and again, nature whispered before it shouted. The muon may simply be whispering once more. But if something truly lies beyond the standard model, what might it actually be? One of the oldest and most ambitious ideas is known as supersymmetry. Physicists often shorten the name to SUSY, partly because the full word appears so frequently in scientific papers that the abbreviation became almost unavoidable. The central idea behind supersymmetry is surprisingly elegant. Every known particle would possess an undiscovered partner, not an identical copy, but a heavier companion connected through a deep mathematical symmetry. Electrons would have selectrons, quarks would have squarks, photons would have photinos, gluons would have gluinos. Even the Higgs boson would gain entirely new relatives. At first, this may sound like unnecessary complexity. Why would nature double its collection of particles? Yet supersymmetry solves several profound problems simultaneously. For one thing, it naturally stabilizes the Higgs boson's mass, preventing quantum corrections from driving it to absurdly large values. Without some protective mechanism, the Higgs field appears strangely delicate compared to the enormous energies expected in the early universe. Physicists call this the hierarchy problem, and for decades, it has suggested that some deeper principle may still be hidden beneath the standard model. Supersymmetry also offers an attractive candidate for dark matter. Remember that everything described by the standard model accounts for only a small fraction of the universe's total contents. Ordinary matter, the stars, planets, galaxies, gas clouds, and every human being who has ever lived, makes up only about 5% of the cosmos. Roughly 27% appears to consist of dark matter. The remaining 68% seems to be dark energy. In other words, the overwhelming majority of reality remains mysterious. If one of the lightest supersymmetric particles were stable, electrically neutral, and interacted only weakly with ordinary matter, it could naturally explain the invisible mass holding galaxies together. Such a particle would drift through space almost unnoticed. It would pass through planets, through stars, through human bodies. Much like the muon passes through matter with remarkable ease, its gravity would reveal its presence, while almost everything else remained hidden. For many years, supersymmetry became one of the leading candidates for physics beyond the standard model. There was just one problem: no one could find it. When the Large Hadron Collider began operating near Geneva, physicists hoped that its unprecedented collision energies would produce supersymmetric particles directly. If they existed at accessible energies, the LHC should eventually create them. Years passed. Countless collisions were analyzed. The Higgs boson appeared exactly as expected, but supersymmetry did not. That does not necessarily mean the idea is wrong. It may simply mean that supersymmetric particles, if they exist, are heavier than expected, or perhaps they interact more weakly than originally imagined. Nature has a habit of reminding physicists that elegance alone is never sufficient. Reality decides. Another fascinating possibility involves entirely new forces. At present, 4 fundamental interactions are known: gravity, electromagnetism, the strong nuclear force, the weak nuclear force. It is easy to assume this list must be complete, yet there is no fundamental reason requiring the universe to contain exactly 4. Imagine growing up on an isolated island where only four musical notes could be heard. Every song, every melody, every instrument, always using those same four notes. One day, someone arrives carrying a fifth note. Suddenly, entirely new harmonies become possible. The universe itself might be waiting to reveal another hidden interaction. If such a force existed, it could subtly influence particles like the muon without dramatically affecting everyday life. Its effects might remain invisible under ordinary circumstances, while quietly altering delicate quantum measurements. Some theorists have proposed the existence of additional force-carrying particles, often called Z-prime bosons. Others imagine dark photons, cousins of ordinary photons, that communicate with a hidden sector of reality almost entirely disconnected from familiar matter. The phrase hidden sector sounds almost like science fiction, yet within theoretical physics, it carries a surprisingly precise meaning. It describes particles that rarely interact with the matter, making up stars, planets, and people. Their existence could remain almost completely concealed, despite filling the same universe we inhabit. Picture two orchestras performing simultaneously inside the same concert hall. One orchestra plays loudly enough for everyone to hear. The other performs almost silently, using instruments whose vibrations scarcely couple to the surrounding air. Both concerts occur in the same room, yet most listeners perceive only one. Perhaps reality itself contains something similar, an invisible sector of particles existing all around us, interacting primarily among themselves, while only occasionally leaving tiny fingerprints upon ordinary matter. The muon might be sensitive enough to detect those faint echoes. Another possibility reaches even further. Perhaps the discrepancy hints not merely at new particles, but at entirely new dimensions of space. For over a century, physicists have explored the possibility that additional spatial dimensions may exist beyond the familiar three. These dimensions, if real, could remain tightly curled into extraordinarily small scales, invisible to everyday experience. Imagine walking across a long garden hose, viewed from a great distance. From far away, the hose appears one-dimensional. You can move forward or backward. Only upon approaching closely do you discover a second direction wrapping around its circumference. Perhaps our universe possesses hidden directions in much the same way. Particles moving through these unseen dimensions could produce subtle corrections to quantum behavior. Again, the muon would become one of the most sensitive probes available. There are even more exotic ideas. Composite particles, tiny microscopic black holes, unknown scalar fields, axion-like particles, entire frameworks inspired by string theory. Each possibility attempts to explain not only the muon's behavior, but many of the standard model's remaining mysteries simultaneously. Yet despite their diversity, they all face the same challenge. Any proposed explanation must satisfy an astonishingly demanding collection of experimental constraints. It must reproduce the Muon anomaly without disrupting countless other measurements that already agree beautifully with the standard model. This requirement is extraordinarily restrictive. Nature allows very little room for new physics to hide. Imagine tuning a piano containing millions of strings. Changing one string by even the slightest amount risks throwing countless harmonies out of balance. Likewise, introducing a new particle inevitably influences many other experiments. Physicists therefore examine every proposal from multiple directions. Does it preserve known particle decays? Does it agree with collider experiments? Does it remain consistent with cosmology? Does it respect observations of stars, galaxies, the early universe? Most ideas fail. Some survive only briefly. A very small number continue to inspire serious investigation. And throughout this process, the muon remains patiently at the center of attention. It asks no questions. It offers no explanations. It simply behaves according to the laws governing reality. Our task is to understand what those laws truly are. Perhaps the anomaly will eventually disappear as theoretical calculations improve. Perhaps future experiments will reveal that the standard model was correct all along. That outcome would still represent a triumph, because science is not about proving our hopes correct. It is about discovering what nature actually does. But if the discrepancy survives, if every improved calculation, every refined measurement, every independent experiment continues pointing toward the same tiny deviation, then future generations may look back upon the Muon the way we now look back upon Mercury's orbit or the photoelectric effect, not as isolated curiosities, but as the first quiet hints that an entirely deeper description of reality had been waiting just beyond humanity's current horizon. And perhaps the most extraordinary part of this entire story is not what the Muon may eventually reveal. It is what the search itself says about the human mind. Because few species would devote decades of effort, billions of dollars, and thousands of brilliant lives simply to explain a discrepancy buried in the ninth decimal place of a single number. Yet we do. And perhaps that relentless curiosity is itself one of the most remarkable phenomena the universe has ever produced. There is a quiet irony at the heart of the Muon story. For most of human history, we believed that understanding reality meant looking outward. We climbed mountains to see farther. We built larger telescopes to observe more distant stars. We launched spacecraft beyond our planet, convinced that the greatest discoveries waited somewhere beyond the horizon. Yet some of the deepest mysteries of existence have not emerged from looking farther into space. They have emerged from looking deeper into the smallest structures of reality. The universe has revealed itself to be astonishingly layered. Every generation has believed it was approaching the foundation. Every generation has discovered another floor beneath its feet. Atoms gave way to nuclei. Nuclei gave way to quarks. Quarks gave way to quantum fields. And now even those quantum fields may not represent the final level of description. The Muon reminds us that knowledge rarely ends. It expands. This pattern appears almost everywhere in science. When Isaac Newton formulated his laws of motion, they seemed complete. They explained falling apples, planetary orbits, cannonballs, tides, and the movement of the moon with astonishing success. For more than 2 centuries, many believed Newton had essentially solved mechanics. Then Einstein arrived. Newton had not been wrong. His equations still describe everyday life extraordinarily well. They were simply incomplete. At very high speeds and within strong gravitational fields, a deeper description became necessary. The same thing happened with classical physics itself. 19th century physicists believed they had nearly finished understanding nature. Lord Kelvin famously remarked that only a few small clouds remained on the horizon of physics. Those small clouds became quantum mechanics and relativity. Entirely new revolutions emerged from problems that initially appeared insignificant. History teaches an important lesson. Tiny inconsistencies deserve attention, not because every anomaly produces a revolution. Most do not. But because every genuine revolution begins as an anomaly. Before black holes became accepted, they were strange mathematical curiosities. Before atoms were confirmed, they were philosophical speculation. Before quantum mechanics transformed science, it existed only as a desperate attempt to explain peculiar observations that refused to fit established theory. The Muon may eventually join that list, or it may quietly fade into history as another anomaly, eventually explained within existing physics. Both outcomes remain possible, and that uncertainty is worth appreciating. Modern society often portrays science as a collection of established facts. Textbooks present polished conclusions. Equations appear neatly typeset. Discoveries seem inevitable in retrospect. Real science feels very different. It is uncertain, messy, filled with disagreements. Progress rarely follows a straight path. Imagine watching explorers crossing an unknown continent. From above, their route would appear hesitant. They would stop frequently, turn around, investigate promising valleys, occasionally follow paths that ultimately lead nowhere. Only after years of exploration would a reliable map gradually emerge. Science advances in much the same way. Theoretical physicists spend years pursuing elegant ideas that later prove incorrect. Experimental physicists devote decades to measurements that sometimes confirm existing theories rather than overturning them. Entire careers may revolve around a single decimal place. To an outsider, this can seem excessive. Why invest such enormous effort into differences almost nobody can perceive? The answer lies in something profound. Reality does not care what humans find convenient. The universe possesses no obligation to reveal its secrets quickly. It does not simplify itself for our benefit. If truth resides inside the 10th decimal place, then that is precisely where scientists must look. There is courage in that. It is remarkably easy to dismiss inconvenient observations. It is much harder to follow them wherever they lead, even if they ultimately prove ordinary. The Muon story also reminds us that science is fundamentally collaborative. No single person solved this puzzle. Thousands contributed. Some designed detectors. Others developed magnets. Others wrote theoretical calculations stretching across thousands of pages. Engineers built accelerators. Computer scientists optimized simulations. Statisticians refined uncertainty analyses. Students calibrated instruments. Technicians maintained superconducting systems. Generations of researchers inherited unfinished questions from those who came before. Knowledge itself became a relay race extending across decades. Perhaps this is one of humanity's greatest strengths. No individual lives long enough to solve every mystery, but civilizations can. Each generation leaves behind better instruments, better mathematics, better questions. The next generation begins a little farther along the path. There is something quietly comforting about that continuity. None of us witnesses the entire story. We each illuminate only a small portion. Together, over centuries, a larger picture gradually emerges. And yet even that larger picture remains unfinished, perhaps forever. Sometimes people ask whether discoveries like the Muon anomaly matter to everyday life. After all, most people will never work inside a particle physics laboratory. Most will never calculate Feynman diagrams or simulate quantum chromodynamics. Does any of this truly matter? In practical terms, perhaps not immediately. But practical usefulness has never been the only measure of human achievement. Music matters, art matters, philosophy matters. They enrich our understanding of existence, even when they solve no immediate survival problem. Fundamental science belongs in that same category. It satisfies something deeply human, our desire not merely to survive inside the universe, but to understand it. That desire may ultimately be one of the defining characteristics of intelligent life. Across billions of years, the universe produced stars. Stars produced heavy elements. Heavy elements form planets. On at least one small planet, chemistry eventually became biology. Biology became consciousness. Consciousness became curiosity. Curiosity built instruments capable of measuring the magnetic behavior of particles existing for only millionths of a second. When viewed across cosmic history, that sequence feels almost unbelievable. The universe has spent nearly 14 billion years assembling beings capable of asking what the universe is. Whether anyone else elsewhere among the galaxies is asking those same questions remains unknown. But here, on this small blue world, the conversation continues. Perhaps somewhere inside another galaxy, another civilization has also discovered the Muon. Perhaps they too wonder whether tiny anomalies hide deeper truths. Or perhaps we are the first minds the universe has produced that can contemplate such questions. We simply do not know. And maybe that uncertainty is fitting, because uncertainty is not the opposite of knowledge. It is the beginning of it. The Muon has not yet given us a final answer. It may never become the revolutionary clue many hoped for. Future theoretical work may ultimately reconcile every discrepancy, or tomorrow's experiments may uncover entirely new surprises that force physics into another revolution. Either outcome would be a victory, because science does not seek confirmation, it seeks truth, whatever that truth may be. As our journey draws to a close, it is worth returning to the place where it all began, not inside a particle accelerator, not inside a laboratory filled with superconducting magnets, not even inside the equations of quantum field theory. It began with a question, a simple question that human beings have asked in one form or another for thousands of years. What is reality really made of? At first, that question seems straightforward. We look around and see familiar objects: mountains, rivers, trees, clouds, cities. our own hands resting quietly before us. Everything appears solid, permanent, almost self-evident. Yet every century of scientific discovery has gently dismantled that certainty. The mountains are made of rocks. The rocks are made of minerals. The minerals are made of atoms. Atoms are made of nuclei and electrons. Nuclei are made of quarks. Quarks emerge from quantum fields. And those fields themselves fluctuate continuously inside a vacuum that is not truly empty. Each layer reveals another. Each answer becomes another question. The deeper we descend, the stranger reality becomes. The muon fits beautifully into this story, not because it is the most important particle in the universe, not because it possesses extraordinary powers. Quite the opposite. Its importance comes from its apparent ordinariness. It should have behaved exactly as the standard model predicted. Instead, for decades, it quietly hinted that something might be missing. Whether that hint ultimately survives or disappears is almost secondary, because the true significance of the moon lies in what it represents. It reminds us that knowledge is never complete. Even our greatest theories remain provisional. The Standard Model is one of humanity's greatest intellectual achievements. It explains an astonishing range of phenomena with precision that borders on the miraculous. It predicted particles before they were discovered. It correctly describes the electromagnetic interactions, allowing light to exist. It explains radioactive decay, nuclear reactions, chemical structure, the behavior of atoms, and nearly everything making ordinary matter possible. Yet the Standard Model also leaves profound questions unanswered. Why are there exactly 3 generations of particles? Why do those particles possess the masses they do? What is dark matter? What is dark energy? How can gravity be united with quantum mechanics? Why does anything exist rather than nothing at all? Each unanswered question reminds us that every map, no matter how detailed, still leaves unexplored territory beyond its edges. Perhaps that is exactly how science is meant to work. Science resembles sailing across an endless ocean. Every island reached reveals another horizon. Every discovery uncovers new mysteries. The destination continuously recedes. Far from being discouraging, this may be one of the most beautiful aspects of existence. The universe appears almost infinitely generous. Every answer becomes another doorway. Every solved puzzle reveals several more waiting patiently behind it. Perhaps reality is not merely complex. Perhaps it is inexhaustible. The muon reminds us of another profound truth. Some of the greatest discoveries begin almost invisibly, not with certainty, with doubt, with one stubborn number refusing to behave exactly as expected. There is courage in following those tiny inconsistencies wherever they lead. The muon story also reminds us that science is fundamentally collaborative. Thousands of people across generations contributed to this measurement, each adding one small piece to a puzzle far larger than themselves. No single person witnessed the entire journey. Together, humanity slowly assembled a clearer picture of reality. Perhaps that is our greatest achievement. Not that we already understand the universe, but that we continue trying. Sometimes people ask whether discoveries like the muon anomaly truly matter. After all, they seem disconnected from everyday life. Yet practical usefulness has never been the only measure of human achievement. Music matters, art matters, philosophy matters, and so does fundamental science, because it satisfies something deeply human, our desire not merely to survive inside the universe, but to understand it. Across nearly 14 billion years, the universe produced stars. Stars produced the elements. Those elements formed planets. Chemistry became biology. Biology became consciousness. Consciousness became curiosity. And curiosity built machines capable of measuring the magnetic behavior of a particle that exists for only a few millionths of a second. When viewed across cosmic history, that sequence feels almost unbelievable. The universe has become capable of examining itself. Whether intelligent observers exist elsewhere among the galaxies remains unknown. Perhaps somewhere another civilization has also discovered the muon. Perhaps they too wonder whether tiny anomalies hide deeper truths. Or perhaps we are the first minds the cosmos has produced that can ask such questions. We simply do not know. And maybe that uncertainty is fitting, because uncertainty is not the opposite of knowledge. It is the beginning of it. The muon has not yet given us a final answer. It may never become the revolutionary clue many hoped for. Future theoretical work may reconcile every discrepancy, or tomorrow's experiments may uncover entirely new surprises that force physics into another revolution. Either outcome would be a victory, because science does not seek confirmation. It seeks truth, whatever that truth may be. So tonight, as you let these ideas settle gently into your thoughts, remember how extraordinary it is that an invisible particle, existing for only a few millionths of a second, has inspired decades of human curiosity. A tiny fluctuation inside the quantum vacuum has challenged our greatest theories, brought together thousands of scientists across continents, and reminded us how much of reality still lies beyond our understanding. Perhaps that is the most beautiful lesson of all. Reality is not a finished story. It is an unfolding one. Every generation turns another page. Every experiment reveals another sentence. Every unanswered question invites another curious mind to continue reading. Thank you for joining me on this journey through one of the most fascinating mysteries in modern physics. If you enjoyed this calm exploration of physics, cosmology, and the deeper mysteries of reality, consider subscribing to Science Sleep Theory and joining us for future journeys into the universe's greatest unanswered questions. Until next time, let your mind wander, let your curiosity grow, and as you drift off to sleep, remember that somewhere in the quiet fabric of the cosmos, countless mysteries are still waiting to be discovered. Sleep well.